Parallel wires lie 7.5 centimeters apart. They both carry 17 amps in the positive x direction. We'd like to find the magnetic field at the position of one wire due to the other wire. So we've seen in the past how we can use a right-hand rule to determine what the magnetic field is like around a current carrying wire. We said that we could grab the wire with our right hand and then just curl the fingers around. This would show us that the magnetic field around that wire would make concentric circles coming out of the page above the wire. So we would have dots up here. And the field would be going into the page below the wire. This means there's going to be a magnetic field coming out of the page at the position of the top wire due to the bottom wire. But by that same token, if we were to use the right-hand rule on, say, the top wire, then the same thing would occur. We would find that there would be X's below the wire and dots above it. Now, a current carrying wire can't exert a field at its own position, but each of these wires does exert a field on the other. In order to find the strength of that field, we should use the formula mu naught I over 2 pi d. That was the field due to a current carrying wire. So let's see, we'll have 4 pi times 10 to the minus 7, 17 amps, and we'll divide by 2 times pi times 7.5 centimeters, which is 0.075 meters. Alright, looks like 4.53 times 10 to the minus 5 teslas. And that's just the strength of it. Now we want to find the magnitude of the force per meter on one wire due to the other. For that, we'll use the formula, the force on a wire equals I L cross B. All right, so what exactly is the meaning of this formula? Well, let's take the top wire, for example. And we'll try to look at it in 3 dimensions. The current is going through to the right, but the magnetic field is coming out of the page toward us. So it would look something like that. That is the B field. Now the wire, if it has a length, we would call that L, but we want to turn L into a vector, so it just has to have the same length as the wire, but the direction that we give it will be the same direction as the current. And now it's a vector. I hope it's clear that the length and the B field are 90 degrees to each other in this situation. So what if we're looking for the magnitude of the force on the wire? Then we would just use I, L, B. Here the angle between L and B is just 90, so it simplifies to ILB. This particular problem, though, it didn't give us a length. So we're going to find the force per meter. And the way that we can do that is by dividing the force by the length. So divide both sides here by L. And then what we get is force divided by length equals I times B. All right, this will be easy to calculate. We'll do 17 amps times the B field we had found. And I'm getting 0.00077. And it'll be newtons per meter because we divided by the length. So every meter will feel 0.00077 newtons of force, which is really not a lot. Now there's going to be a symmetry to this situation. If the top wire feels 0.00077 newtons per meter, the bottom wire is going to feel the same force. But what will be the direction of these forces that the wires feel? Which way will they be pulled or pushed in this situation? Well, that's where the cross product comes in. We want to let our pointer finger be the current or the velocity of the moving charges, or L. They have the same direction. For the top wire, it's going to be to the right. The middle finger will be the B field direction. And the result, the thumb, is going to be the force on that wire. All right, so let's take a look at this for the top wire for just a minute. Point your finger in the direction of current. Let your middle finger come out of the page. And which direction is the force on that wire? The force is down. Now do the same thing for the bottom wire. Point your finger in the direction of current. And let your middle finger go into the page because the upper wire creates a magnetic field into the page. And which direction is the force on the bottom wire? It will be up. So the top wire is pulled downward, but the bottom wire, by symmetry, is pulled upward.